Good afternoon, everybody. And thank you for joining this keynote presentation by Hans-Peter Arp. I'm very pleased to introduce you. You are Hans-Peter, an expert advisor at the Norwegian Geotechnical Institute since 2008, but you're also a professor at the Department of Chemistry at the Norwegian University Science and Technology Institute, NTU in Trondheim. And you have a background in environmental chemistry from ETH Zurich. And I've known you for a long time, actually, because you've worked in the area of PFAS. But in the recent years, you've worked on the waste effect project, on the sludge effect project. And then in later recent years, you have started to work on these persistent and mobile substances, of which you have been really a key driver for making attention, both in the scientific world and in the policy world, and making sure that to support the policy level, to get it into the chemical strategy for sustainability. So now we have an action to get it under the CLP. So today we are very pleased that you will present to us on the title Towards Reducing Pollution of PMT and vPvM substances to protect our water resources. And with that, welcome very much and welcome to the audience. And we're looking much forward to hear more about how we can protect our waters. Welcome.
Well, thank you very much, Jenja, for that nice introduction. And thank you also to the SETAC organizing committee to allow me the opportunity to present the keynote on this important topic. So the flow of my keynote will happen in three waves. On the first wave, I want to tell you about the increasing contamination that Europe has been experiencing from PMT, vPvM substances. In the second wave, I'm going to tell you about the regulatory developments that Jenja was talking about, to give you the overview of the status and where the future could go. And the third, this is the most important part, it's about how we as a SETAC community, representing industry, regulators, academia, NGOs, could work together towards reducing pollution. So wave number one, the increasing contamination. This is a quote by a very active member in SETAC, Pim de Voogd. He wrote in 2008, the European REACH legislation will possibly drive producers to innovate their products, possibly to develop newly designed chemicals that will be less persistent, bioaccumulative, or toxic. This may result in higher mobilities of chemicals in the aqueous environment. As a result, the drinking water companies may face stronger demands on removal processes as the hydrophilic compounds inherently are more difficult to remove. That was said in 2008. Let's fast forward to the present day. And these are results from a very important drinking water source in the Netherlands. And the purple dots on your screen, the size of them indicate the number of persistent and mobile organic compounds they have been observing in that drinking water source. And the black ones represent those which they think have exceeded a threshold concentration which is dangerous to their consumers. So this has been increasing. And on the y-axis, those are the costs. It was something called a removal requirement index, but how much money they would have to invest in order to keep that water drinkable. And this has been increasing because of this increasing contamination. And how does this happen? Just to think conceptually, chemicals, they're made in many places in Europe. They improve our lives in many ways for various uses and products. But whether in the synthesis phase or the use in the product phase, there are sometimes emissions. And if those emissions are transported through the environment to eventually a place where they hit water treatment production, they could penetrate that water treatment production and then enter my son's drinking water bottle on the slide here. But what are the properties of a contaminant that can make that kind of journey? They have to be persistent and mobile, persistent so that they don't degrade, and mobile so they actually move. And if they're also toxic, we got a problem that we should address, and that's what we're doing today. So just to give you some examples, this was a survey of PFAS and global tap water taken from cities around the world. And I can compare that, since we're here in Copenhagen, with the Danish drinking water limit of 0.002 micrograms per liter, 2 nanograms per liter. So we can see already from this survey, based on that level, there are several cities that have drinking water contamination that the Danes would not consider safe. Montreal, Quebec, Toronto, Chicago, Ouagadougou, Tokyo, Paris, every continent. That's one example. Another one is this, and this is a trifluoroacetic acid. There's a lot of discussion about that today. This is a report of a survey done in Denmark, where they did a survey of 247 groundwater wells throughout the country, and they found trifluoroacetic acid in 219 of them, up to 2.4 micrograms per liter. We have data for other countries as well. In Germany, they found it in tap water up to 20 micrograms per liter, in river water up to 120 micrograms per liter. And in China, there's a survey where they looked at in the blood, and they found it in 97% of those sampled with a median concentration of 8.5 micrograms per liter. Where did this TFA come from? There is, it's called a substance of multiple sources. There is actual production of TFA, but there was also a good session, the PMT session earlier today. They were talking about how some pesticides that are produced, or plant protection products produced at high volumes, have TFA as a transformation product, but also at even higher tonnage levels are refrigerants put in the atmosphere that degrade in the atmosphere to TFA. And so what you can see now is you get TFA accumulating in the global ice cores, along with other short-chain PFAS. So these are accumulating, and all evidence posed that this is synthetic origins, not natural origins of TFA that's accumulating right now. So the lowest non-observable effect concentration that I could find is for this microalgae. I'm not going to try to pronounce it, but it's 120 micrograms per liter. But we can't think that if contamination ever gets to a point where we have more remote regions approaching some kind of effect concentration, there's no way we can reverse this. It won't dilute. It's already diluted. So we'll be here for generations. So that makes it meet the criteria of being a planetary boundary threat. But it's not just PFAS we're talking about. Those are the most well-known, but here's some other examples. Melamine. Melamine you can find in drinking water up to 2 micrograms per liter. And this is a compound that's nephrotoxic in combination with another chemical called cyanuric acid. And we can find cyanuric acid in water too, up to concentrations of 0.12 micrograms per liter. Another one is dioxin, 1,4-dioxin, commonly measured in many drinking waters, at concentrations up to 0.8 micrograms per liter. And benzotriazole, this is often used as a fungicide in dishwashing detergents. And this is commonly found in drinking water at concentrations up to 0.2 micrograms per liter. And to refer to the Danes and their limits, the limit they said is 0.02 micrograms per liter. So these are things that we can be in exceedance of. And there are many, many, many more. But an issue that was raised earlier in 2016 was there's a lot of gaps to analyze these compounds, especially an analytical gap and a regulatory gap. So at the top, these were log D values of what you can measure in, say, non-target analysis or suspect screening with GC and RPLC methods. And at some point, things get so hydrophilic based on the log DOW value that these methods don't work. And then you looked at what chemicals had regulations about them at the time, like the Stockholm Pulp Convention. They all kind of landed on this area where you could easily measure. For these methods over here, you needed dedicated methods. But since then, recently, there's been a revolution, I would say, in new techniques in analytical chemistry to measure these very hydrophilic chemicals. There's technologies like hydrophilic interaction liquid chromatography, or HELIC, ion chromatography, capillary electrophoresis, and superfluid chromatography. And these are able to separate these very mobile substances. And of course, along with that, you also need novel enrichment techniques, because when you're trying to get them from water, they're kind of coming up the same place as your ions, like your chloride and your fluoride and your bromide. So you have to enrich them as well. And now we can really move on. Now we can make suspect screens suspect screening lists of chemicals that we might suspect are in drinking water or water resources based on their persistency and mobility, and that's something we did here. But also you can look at emissions. What do we know about what those chemicals are used for? And there's also some PMTs on the ChemStack 10 list, so we got chemicals we can look out for. And then when we find we use these new techniques, we're getting lots of positive hits. And this has been a real, well, in some ways exciting success story, but also a troublesome finding. These are chemicals that have all been discovered in the past, like maybe 3-4 years, at high concentrations or being ubiquitous, thanks to this new way of suspect screening and these new analytical methods. I won't go through all the structures, but you can kind of see why they're persistent. You got these very complex cyclical structures, which are hard to break down, a lot of benzene sulfonates, a lot of guanidines. These two are used in car tires as compounding agents, so there's a lot of focus on car tire particles today. So these are all chemicals that we have found recently. But now that the analytical gap has largely closed, we still have a monitoring gap. So this is survey results of an upcoming study where we went to 27 analytical labs in Germany, and we gave them a list of 150 PMT substances, and said, which can you analyze in your lab? And so here there's 27 substances where more than 20% of the labs monitored regularly. So there's no monitoring gap for these, really. And there was 39 that less than 20% of labs monitored regularly, so maybe a bit of a monitoring gap, but we're at least getting some data. But then there was 58 substances that nobody was looking at, but they said they could if you asked us to, or if you paid us to. And 21, they can't analyze it today, but they would know how to do it. They could put some ideas on the table and try to figure it out. And there's 5 compounds that all 27 labs said we have no way of measuring this. So there's still a little bit of an analytical gap also. And there's a remediation gap because there's no drinking water technology that can remove all these substances. Every technology will have a limit. Activated carbon will not get the small aliphatic or the ionic compounds. Anti-exchange resins are not good for cations. Cation exchange resins are not good for anions. Reverse osmosis, nanofiltration, these are our 2 most effective and expensive techniques. But even then, there's still some molecules that will break through. And you can also use advanced oxidation processes, but then you have to look for potential byproducts, which can also be persistent and mobile. And so we did a survey, too, of the same 150 substances that we did this survey on the monitoring gap. We also asked the drinking water companies, can you remove these substances? And we also did some own theoretical studies of these 150 substances, which were removable with ozonolysis and activated carbon. Most of those were not effective with ozonolysis or activated carbon, meaning you'd have to use something like reverse osmosis or nanofiltration. Some of them could only be treated with ozonolysis, some only with activated carbon. And there were some that were actually easy to remove. So there is a remediation gap. And so you can think, what would be the cleanup costs if we really wanted to clean up? Now, I'm going to just give you some numbers just to say a maximum extrapolation. Now, a number for how much it costs to use reverse osmosis or nanofiltration, it's usually about €1 per cubic meter at scale, and with an energy usage of 1 kilowatt hour per meters cube. So if we take numbers like there's 200 billion cubic meters of industrial wastewater in Europe, that's about 200 billion euros a year for water treatment, if we had to go there. Or even if we just did drinking water treatment, there's about 38 billion cubic meters a year of drinking water in Europe. That's 38 billion euros. That's a lot of carbon emissions that we'd be talking about. And then you also have to think about issues. Would you want all the water in Europe to be treated with reverse osmosis? What happens to mineral water? Every water will just be essentially synthetic. But I don't even think that's even possible anyway. It would take forever to upgrade European water resources to use reverse osmosis. It's extremely expensive. There's a lot of infrastructure and logistic hurdles. So that was the first wave of the increasing contamination. So what were the regulatory developments that have been going on in parallel to address it? So I'm going to start this section with another quote from around the same time as the first quote I gave from Pim de Vogt. This quote is by Michael Neumann. He's sitting right here. The evaluation of drinking water impacts is not yet explicitly defined in REACH. There should be screening criteria developed for which the responsible authorities could identify the chemicals that could impact drinking water from the database of REACH registration database. That translation was mine, and I put database twice in the same sentence. I apologize. To realize the precautionary principle, it is important to identify the potentially drinking water contaminants as early as possible. So this was a way to use REACH to get a hold of these substances. How do we consider drinking water? So the first time this idea was presented was actually a SETAC meeting in 2012 at the German SETAC GLB, but it was kind of presented to the larger SETAC Europe 7 years ago at the 2015 meeting. And from the beginning, the PMT concept was designed to be hazard-based. And the way to do that was to introduce 2 new hazard categories: persistent, mobile, and toxic, and very persistent and very mobile substances. So for that, we needed to develop criteria to see if substances were a threat to the sources of our drinking water so that we could minimize emissions of these substances through risk mitigation measures. So one of the ways that you go about developing a criteria is show how it's similar to other criteria. So one part of the argument why this criteria was needed was we, with colleagues Michael and Sarah Hale and Ivo Schliebner from UBA, we wrote this paper that says all PMT vPvM substances pose an equivalent level of concern to persistent bioaccumulative and toxic substances and very persistent, very bioaccumulative substances. And this was based on 16 categories on their health effects, their environment effects, and other environmental effects. And we used 3 case studies, PFBX, Gen X, these are 2 PFAS, and 1 for dioxane. And while the time we were writing it, and now after we were writing it, all these chemicals, these 3 case studies are now officially considered by REACH to be an equivalent level of concern to PBT, vPvM substances. Just briefly on how the argument looks like, we could argue in both there's a possibility of irreversible health effects. PBT compounds will bioaccumulate in humans, and chronic and acute effects are possible. The only thing that's different with PMT compounds is the exposure route. So yes, continuous exposure through drinking water and remote aquatic ecosystems over long time scales are possible despite rapid excretion rates, so chronic and acute effects are also possible. And the exposure is also irreversible, like the example with TFA. There is no dilution once it gets to a certain point. And just like it's hard to dilute a PBT substance in the food chain. So how do we set criteria? Well, it's important in this to establish that persistence and mobility are substance properties. So this is how a typical groundwater contamination might occur. Here's an industry emitting into the soil. It goes to the vadose zone, enters the groundwater, and then you get a plume formation. And usually here you get your most mobile substances, and back here your least mobile substances. So the more mobile they are, the quicker they will end up in this fellow's drinking water. So this was something that was looked at since the late 80s, and there was a fellow by the name of Gustafsson who developed the Gustafsson ubiquity score, showing that he could plot which of the chemicals that were the most significant groundwater leachers as a scale of their simulated soil half-life in the lab, so 10 days, 100 days, 1,000 days, and something called the log KOC value, which is the organic carbon water partition coefficient. So you end up with this zone here of things that hardly absorb to soil at all. They can reach this drinking water well very quickly, and so they can have a relatively short life before they degrade to get there. If it sticks to soil, even better. It'll need a longer half-life to make it to that well, but it would eventually make it. There's not a clear boundary between a leacher and a non-leacher. There is this transition zone in the middle. So starting with this type of theoretical background, very briefly, there was 2 documents that were sent out in 2019. These were showing this new criteria for PMT vPvM substances, and this was the scientific background. So how it works, essentially, is following the REACH, you have to look if a substance is going to be introduced in REACH at a certain tonnage. You evaluate if it contains an organic chemical above 0.1%. And if it does, then you have to do a persistency assessment. If the chemical is not persistent, we don't have to discuss if it's a PMT or vPvM anymore. It's not persistent. But if it is persistent, we have to look for mobility. And if it's mobile, if it's not mobile, it's not a PMT vPvM substances. We're done with the evaluation. But if it meets the mobility criteria, it could either be a vPvM substance or a PM substance, depending on how these 2 evaluations turned out. Following this, you look for toxicity, and then the substance could either be a vPvM in PMT, or alternatively, just a PM, and then it wouldn't be a PMT vPvM substance. So what are these criteria? Well, for persistency, it was quite easy. We just used the REACH, or UBA suggested just to keep using the same criteria that have been established for PBT, vPvB compounds, which is showing the half-life in different media. For instance, in soil, this is 120 days for persistence and 180 days for very persistent. So you can think of where that might be on that Gustafsson plot I showed earlier. But we can think of other things as well, like fresh water, obviously, because we're talking about water pollution in this case, and freshwater sediment, because one other pathway to drinking water is that you're in a river, it's going through the bank filtrate and into the water resource. There's also marine sediment there and marine water, and there were some discussions if these are relevant for PMT vPvM, but it's actually easier to keep them on there because if you have any type of data that can indicate persistence, that can help in a weight of evidence, and it's much harder to argue why this should be removed, actually. And then for mobility, the criteria that where it was put on the Gustafsson type of chart was to set the definition of mobile for an experimental log KLC value with this pH range, because some compounds are ionizable and their absorption depends on the pH, as less than 4.0, that's a log unit, and very mobile as less than 3.0. But since then, this criteria has actually been taken up by the European Commission for the CLP regulation, and at the last time I checked, they wanted to move these to lower values, so less than 3.0 for mobile and less than 2.0 for very mobile. So where did these thresholds come from, other than that Gustafsson plot I showed earlier? Well, an important one was just empirical observations. I showed you there were chemicals in drinking water, but what were their KOC values? And what you can see is if you plot their log KOC values versus the number of substances monitored in drinking water, you get this really big drop-off at the log KOC of 4.0. There are some chemicals that have higher log KOC, but these are often explainable by very local contamination, such as being present in the plumbing material, like large phthalates, for instance. And then we have, as for this criteria of here of 3.0, which the UBA criteria would be very mobile, and the European Commission's draft criteria would consider mobile, you still get most of the substances. You're just giving these substances basically a free pass if you switch to the European Commission's criteria. So, but there's other reasons we could argue for this criteria. It's been used as a threshold in many different contexts, such as the EU Common Implementation Strategy Working Group for Groundwater, which is very important for developing the groundwater directive. The biocide regulation also has a kind of a cutoff around that log KOC. The United Nations Food and Agricultural Organization, they also have this scale based on persistency and KOC values. So we have a lot of successful backstory to show how this could work. And also leaching tests, because we find often that leaching test results correlate very nicely with KOC data. What's also not in this, what has to go into this discussion is the impact assessments where we put that. Because if these chemicals aren't included, that will affect how these chemicals would be on the market. This would have economic considerations, and we have to balance it with the health, remediation, and removal costs. And that's where the discussion is at the moment. But how many PMT, vPvM substances are out there? From a recent survey we did, and we'll publish very soon, we conclude that if you use the EC criteria, it's about 1.9% of the REACH registered substances. If you use the UBA criteria, it's 2.6%. However, I have to caveat with the fact that for most of the compounds, we couldn't do any preliminary conclusions because we lacked the data of the data sufficient quality. So, but compare that to the ones in drinking water, it's 18% of the chemicals that were monitored in drinking water would be considered PMT, vPvM. So these would be the most problematic ones to remove. Not all of them, just the most problematic ones. And with the UVA criteria, it's 25%. But here too, there's a lot of chemicals we monitor in drinking water that we don't know their persistence or their mobility. So these were the developments, and like, where's the future going to? So this is just an overview of how these criteria were just developed over the years, and Michael Lyman has a very good poster that goes into more details than this one, showing all the working group discussions at the EU level that were used to make these criteria. And now it's advanced to this very exciting stage as part of the EU chemical strategy, where they're going to introduce this new criteria into the CLP regulation and the REACH regulation. And the next step after adoption there would be to try to get it into the United Nations GHS level. So this would be a criteria that's used as a hazard assessment throughout the world. So that's the second wave, regulatory developments. Now comes the most important one. What we can do as a community towards reducing pollution. So I want to compare two things. I want to compare the toxic-free hierarchy of the chemical strategy of sustainability with Pandora's box. And we can imagine that she's got a bunch of PMT, vPvM chemicals in there. You can't get them back in. But so what can we do that's different than what Pandora would do? Well, one thing that we have to do, since all the EU Green Deal, as part of the EU Green Deal, all the environmental regulations are opened up for discussion, we have to ensure that they're properly harmonized around their approach to PMT substances. So on the scale of prevention to safe and sustainable chemicals, we do have the REACH and CLP regulation, but there's also the talk of the PFAS restriction, which would cover a lot of these chemicals. There's the essential use concept. Do we need to use these PMT, vPvM chemicals? And safe and sustainable by design, to kind of design our way out of using these chemicals. So these are being developed. But if they don't work, if they become essential, if emissions are unavoidable, then you can use other regulations to minimize and control, such as the Kiev Protocol, the Aarhus Convention, the Industrial Emissions Directive. So what you could do is put them in the registry for emissions, the EPRTR registry, so that companies that use these chemicals have to report their emissions, and then we can develop ways to control them. And finally, if that's not working out, you have to go through these eliminate and remediate regulations, such as the Urban Wastewater Directive, the Sewage Sludge Directive, the Water Framework Directive, the Groundwater Directive, Drinking Water Directive. We just have to ensure that it's a consistent strategy at the three levels. But I'll go a little bit into eliminate and remediate. So the conventional methods that we use, the cheap ones, the ones that don't cost much, the ones that are mostly common available, such as bank filtration, aeration, sand filtration with sedimentation and coagulation, they are cheap, but they are ineffective. And they also can emit PMT, vPvM substances, such as aeration can launch them into the atmosphere. And we still have to, if we're doing coagulation and filter pressing and sludge formation, we have to look at the sludge treatment as well. But for most of these PMT, vPvM substances, we have to look at techniques like film foam fractionation, which is a new exciting technique. or activated carbon ion exchange or nanofiltration reverse osmosis. And often you need these in a treatment train because one technique won't get all, but sometimes it's more efficient to put them in different orders and configurations to optimize their effectivity. But as you go from one to the other, your price will increase to that dramatic number I presented earlier. And even with these new techniques, you still got to think about the concentrates, because in all of them, on the activated carbon, the nanofiltration, the film fractionation, all the PMT and the PFAS, they'll all go into some kind of concentrate that you have to treat. And I'll recommend this great presentation today by Santa Smith, which showed some film fractionation if you want to hear more about that technique. Now, what to do with those brines? And there's new techniques here, but these are research frontiers. And we don't know much about them. They're in development, but you can use catalyzed electrolysis and oxidation, but how to optimize the byproduct formation, the energy consumption, that's a technology frontier. That's an innovation frontier. How to deal with adsorption on activated carbon. We can optimize incineration and pyrolysis methods to regenerate the activated carbon and remove all the PFAS. But then we have to look at what are the volatile emissions, again, coming from these processes. What is the energy consumption? It's not zero. Or we can landfill. And this becomes the usual landfill problem. Nobody wants a landfill in their backyard that's a PFAS depository. But you still got to look at long-term leachate emissions from such landfills. Going over to minimizing and control, one successful strategy that I like this a lot, what they do in Sweden, is called the REVAC control. And this is where you get different stakeholders working together to do the source control of emissions. So first, like the water companies that are producing the water, they will monitor for PMT, vPvM substances. And if they find something, in this example, they would go upstream to find the source. So maybe they have PFAS and identify an airport or a landfill or something. And then they would find that site owner, and then in collaboration with all the relevant authorities, they would sit together and they'd work together about how they could remove those sources upstream before they contaminated the drinking water resource and all the environments in between until it got there. And this is where regulations like the EP-RTR registration could also help. So this is called source control. Other thing we have to do is keep working on that monitoring gap and actually keep working on the analytical gap. This is a recent paper by Isabel Neuveld and Daniel Zahn and colleagues, where they were showing how they could find more suspect screenings list based on the same principles I showed earlier. What substances are being emitted, what's their persistency, what's for mobility, and we're getting better at actually finding these new compounds that we haven't found before, and also collecting data for the chemicals that we have a little bit of data for. So you have to keep doing that. Another thing we have to do is prioritize. I have a poster about this today, but this is based on the PMT vPvM hazard. You can look at other things about the chemical to say, should we take care of this first? Is this the ones that we should deal with first? And you can look at things like, are they being emitted? What's the status of the analytical and monitoring gap? What's the status of the remediation gap? What's the status of the prioritization level? So you put this all together, and then you make a prioritization level, I should say. So I'm not going to read every box. I'll just show you some results. So these are chemicals that we would put as the highest priority to make a strategy about now, like melamine or 1,4-dioxane, PFBS. These are the ones that are most commonly in the drinking water, like the drinking water here on the table. And we also, for the local scale, this is also part of source control, whether it's a landfill or an airport or wherever, or wherever these PMT, vPvMs, or an industry emissions, we have to get better at our models. And these are really, really hard, some of these substances, especially if they're ionics. For instance, PFAS, there's been a lot of research now about how it absorbs to the air-water interface. This is a complex sorption phenomenon that makes it actually stay in the unsaturated soil longer than expected, but when it hits the groundwater, it transports like we expect. But even that is kind of complicated. There was a nice presentation from Michel Hubert today about how in the groundwater the PFAS would like to absorb to the small fibers that are there. And also, like, you have to also make these multimedia models, which are extremely challenging for ionic compounds, but this is what has to be developed, particularly at the local scale for risk assessment and remediation projects. So let's get into the top. Let's get to the lid of Pandora's box. Safe and sustainable chemicals. So there's different ways to do it, but one of the most important ways is to increase the market for PFAS and PMT, vPvM-free alternatives. So there's some resources in place for that, but I'll just say one thing is we have to expand the notion of green chemistry to just not include things like it's not volatile or low CO2. We should also consider, is this chemical biodegradable? Is this chemical non-toxic? And there's also safe design as well. Can we replace the products that we know emit PMT, vPvM substances with products that don't? This is a material science solution. And we can also take in the essential use concept. And a very thought-provoking thing from this paper by Julian Gluga, Rachel London, and everyone involved was that is performance of a product necessary? Like, do our bike oils need to be so slippery? Do our ski glides need to be so fast? Can we live with lower product expectations if it's better for the environment? And this is a resource that is made by ChemSec, where people who are having businesses and they want to phase out their hazardous compounds, their hazardous PFAS and PMT, can get an exchange with other people who are trying to do the same, maybe with designers who can help them with that. So if you're in industry, that's a great resource to use. The other thing is we have to develop our alternative assessments models to avoid regrettable substitution. So these are various alternative assessment frameworks like Green Screen and the US EPA CTSA. What they all had in common was none of them included mobility, but now they should. And with the PhD student Ji Zhang, we developed a way to include mobility in these assessments. So it's just something that we have to have on our radar when looking at chemical alternatives. And the other thing, we also have to start grouping things because there's so many chemicals that are out there, so many potential PMT, vPvM substances. How do we get a hold of them? An important way is substance grouping. Well, what's an effective way to group them? Well, one way is we could start grouping chemicals based on their known precursors. For instance, we talked about trifluoroacetic acid, and we showed how it's a degradation product of many different things. But should a comprehensive TFA strategy account for what are all these precursors doing? How do we develop that? Or do we look for read-across approaches? So over here we have an example of triazines. So these are all PMT, vPvM substances, cyanic acid, melamine. I had these as my examples. They're in drinking water. Atrazine, not so much in drinking water these days, but it's still an issue. And chiromazine, which is and sometimes in drinking water. But we could all group these as PMT, vPvM substances. Do we need a triazine strategy? That's a question. Or another question is like a PFAS strategy in general. Emma Szymanski recently found on PubChem there's more than 6 million OECD-defined PFAS. Like, we can have a PFAS restriction, but when we're talking about numbers like that, how are we going to group them to have a unified strategy? And we have to fill the data gap, obviously. So there's some really interesting discussions about what is persistence and how to move persistence in the 21st century, and what is the best way to approach persistence from a practical point of view for everyone. And I would say, like, my point of view is it's easiest to work within the framework we have now. The problem is persistency measurements to get those simulated half-lives are very expensive. They're very time-consuming. So there are ways of doing things simpler, and I'm just going to highlight this study. And this was a way that showed that instead of using carbon-14 labeled standards, you could just use it benchmarked to a well-known chemical whose biodegradation behavior was well established. In this case, it was aniline. So the aniline was just spiked at the same time as these compounds, and then they could extrapolate the simulated half-life with the OECD 309 test. And all these chemicals that we suspected of being very persistent were confirmed to be very persistent. And that's also, these came from the same UBA report in 2019 that was the motivation for that study. But see, as you see here in REACH, there's over 5,500 substances where it's almost impossible to make any type of persistency judgment. The same with mobility. You have to fill the gap. Now, I think if you got experimental KOC data from the field, that's the best data that you can get. And we know that, but we don't have KOC data for all substances. For neutral substances, I'm not worried at all because we know that the KOC models work very well for neutral substances. And estimated KOC data, I think they also work at the screening level. Like if you're just trying to hit within an order or two of magnitude, you can use estimated KOC values quite successfully, but for the local scale, you'll have to understand the dynamics of these ionic compounds. Like as I talked about the PFAS, their absorption to the air-water interface, for instance. So there's a lot more research that needs to be done at that level to understand the mobility in soil. And if you want to get an overview on that, I would recommend this review that recently came out by Gabriel Sigmund, ES&T, who's here in the audience right now with us. But for now, we're just recommending the standard for mobility assessment is just to get more data, get soil, get samples, do a batch absorption test. Toxicity should also fill the data gap. There's a lot of talk in SETAC recently about novel approach methodologies or new approach methodologies for chronic exposure parameters. So how do we get chronic PNEC values for fish? These things have not been that well studied because these bioassays are hard to make for these very mobile substances. But one interesting, thought-provoking thing is if we would consider the vPvM assessment a NAM. Why? Because it doesn't involve animal testing. And if we already have reason to suspect that vPvM substances are problematic because of this exposure, we can already start to regulate them without investing money in the toxicity testing. And for grouping substances together, we have to develop, we have to consider, sorry, I should say my next point. The next point is what do we do about these planetary boundary threats? Do we consider planetary boundary or global accumulation potential as part of a toxicity assessment, meaning that we have to be even more cautious where we set the thresholds if this chemical showed an ability to accumulate globally without any chance of dilution? That should be something that I think should be discussed along toxicity. And then we should also work to group them together, what we know about the toxicity of similar substance groups, like PFAS substance groups, triazine substance groups I showed earlier. Should we develop relative potency factors for the different members of such groups? I think these are important ideas to pursue as we address lowering pollution of PMT, vPvM substances. But ultimately, we need brave new markets for biodegradable, non-toxic chemicals. And we have to get venture capital here to help us. I mean, I'm pretty sure the case could be made to any funder, to any well-funded pockets, that people want to buy safer products. People want to buy PFAS-free products. Where can we get the money to push that forward? But we should also remember the other elements that are important in that, and these are the social science aspects. Like how do we get consumers to tailor their choices towards safer options? We should involve psychologists to make these mental models to understand why do people choose to buy something with PFAS versus something without PFAS, or why do they go for this product with that leaches melamine versus that product that doesn't leach melamine. These types of choices. And obviously we need more communication in SETAC with material and designers. We're often looking at what the chemicals do in the environment. We don't have the perspective of the people who are actually making these chemicals and making these materials. And we should have more dialogue with them because we are living in two totally different worlds and we should work in the same one. Okay, so my conclusion is essentially that we have the tools now already to reduce pollution to PMT, vPvM substances. All you need is love, obviously, but you also need venture capital, new markets for safe alternatives. You need PMT, vPvM, and CLP and REACH with a consistent policy framework with the other regulations. You need more science, more transparency on PMT data. Those are the safe and sustainable ways to go forward. Minimize and control, we need to include these substances in emission source control and registry so we know how much is being emitted and how to minimize this. And we need prioritized action, especially towards vulnerable areas of Europe, the planet and for the planetary boundary threats. Those are the most critical to address. And of course, with eliminate and remediate, we still need to work on innovative, low remediation treatment trains. There's a lot of innovation to go on in that sector as well, so it wouldn't be as expensive to remove it if we had to. So those are the ways forward. And so I just want to acknowledge the funding that was behind all this information I presented. It started with being involved in this Water JPI Promote project in 2014, led by Torsten Riensma and Urs Berger. It then led me to work with the Umweltbundesamt and this German-funded projects, research and innovation products, from 2016 to today. And more recently, we started working on these Horizon H2020 projects. First, Perforce 3, where we have 15 excellent, truly excellent PhD students working on ways to understand and solve PFAS, and most recently, the Zero PM project, which I'm deputy coordinator of. And if you want some more info and recommendations that are a little bit fun than dry literature, I really recommend this podcast that the Perforce 3 PhD students are doing. It's absolutely amazing. There's a lot of updates at this Umweltbundesamt website, where very soon there should be some new reports on these substances that are very exciting. I gave you a sneak preview of some of the data here. And on the zeropm.eu page, we got a lot of fun things. We got videos, we got newsletters. You'll absolutely love it. So I totally recommend checking that out. Okay, and now with that, I want to say thank you. That was my last slide.
Thank you very much. And now then the floor is open for questions. And I see the first hands. I see one up there.
Gabriel Siegmund from the University of Vienna. Thanks, Hans-Peter, for this really amazing talk. I was wondering what your feeling is about using big data and chemoinformatics to help us prioritize and group this, jungle of chemicals that we need to find ways to deal with.
Well, I think that's cheminformatics is the only way forward with looking at the variety of chemicals that we have to face out there. I mean, we don't have the tools to monitor everything. We don't have the tools to regulate anything, but I think through cheminformatics, it can help us in two ways. And one is to both find from various databases, from use databases, emission databases, what are the chemicals that are most likely out there at a high level and posing the most threat. That's one way, but it can also train us to come up with these ways of regulating groups of substances or mixtures of substances rather than one substance at a time, as we've been doing up to now. Thank you for the question.
Good. And then I think there's another one up there.
Hi, thanks. Very nice talk. I was wondering, do you think there is a clash between the reduction of pollution and a society that is based on exponential growth?
Obviously, yes. But I think there are ways to optimize what we are doing now and how we can live better. And this is our more fundamental sociological questions. But I mean, I do think that we have to think about focusing on, sure, radical system change and what we value. And I think that is important, but this goes beyond what I talked about today. But I absolutely agree that this is the level of conversation we should have. Yeah.
Yeah. Are there other questions from the floor? There's one down there.
Hi, thank you for this inspiring talk. Ioana Katsiadaki from CIFAS UK. On the last option on removal, I think a lot of countries are putting hopes for chip technologies based on nanomaterials, nanotechnology in general, which again, it might have its own issues in terms of safety assessment. Would you like to share with us your thoughts on this?
Yeah, I know there's a lot of research and development on these fields, and it's always a lot of questions how these will develop at scale. So we never know, like some of these technologies cannot be scaled up. But in general, I think I have I have a preference for simple, not so expensive technologies. Like, this is why I like the foam fractionation. It's just air in a tube. And if you want to make it super good, you can put some surfactant, but you got to study the surfactant. So it's generally the more complicated the technology, the more questions you have to ask. And there are simple technologies, and I like those better. Yeah.
Are there other questions? Otherwise, I know Senior has one, at least.
Yes, at least one. Thank you, Hans-Peter, for this very also comprehensive overview of the story behind the PMT and vPvM, and also why it makes sense to address them upstream. So in looking at the posters today, I came across a poster that talked about some plant toxins that are used as biopesticides. And we know that we have the Farm to Fork aim under the European Green Deal to reduce 50% of the use of the chemical pesticides. And these biopesticides are being discussed as being some of the alternatives, either as extracts or crops grown in the field. An example is the pyrrolizidine alkaloids, for instance, used in ragwort. And some of these compounds are persistent and mobile and toxic. Do you think they should qualify, or would they qualify under the CLP, or what should the approach be to these compounds?
Yeah, well, this sounds like more like a regulatory question, but I'm learning this kind of now. But like from my point of view, like this hazardous assessment should happen in the absence of what the chemical is being used for. Like theoretically, every chemical should have its hazard assessment. And then when you talk to me about the next thing, about what is that chemical being used for, regardless of where it's from, in this case, it's a plant production product, then we have to have that conversation after, in my opinion. And then we can talk about that specific question, because just as we have to separate the chemical hazard and the risk, and what it's being used for falls into the risk assessment.
Okay, so in other words, it's like, because it's a hazard criteria, you take it up front, and then only after you discuss the uses.
Yeah, and I think it's better, it's easier to just do that. We put all chemicals on the same framework, whether it's a CLP, and then after that, when we find out what the chemical is actually going to be used for, then we can have that level of conversation. And then we can make strategies. There's never one size fits all solution.
So there's another question up there, and after that, there's one down here.
Yeah, also thank you for your talk. I'm Banwood, German Environmental Agency. I was just wondering, because this concept of mobile compounds is just dealing with the aquatic environment, if you should not think further and also include the atmospheric transport. Because this is also a case of mobility, I would think.
Yes, I agree. I mean, I agree that's an important thing. But for me, atmospheric transport is taken quite well with the LRTP long-range transport potential from the Stockholm Convention. So if you wanted to include that, or just use that as in something else, and have the M as it's being defined now specifically for water, and just take the LRTP plus that, so you could have a PBMT LRTP substance, which are just lovely.
Okay, and then there was one down here.
Yes, I'm Catherine Fenner from Eawagen, University of Zurich. Thanks, Hans-Peter, for a really nice talk and a lot of inspiration. One thing you actually mentioned to me this afternoon, but it came up in your talk again, is it just made me realize again that there is persistence for different reasons, right? So, and I guess I've also been promoting that we should also factor in or consider bioavailability in assessing persistence, and that there is such a thing as intrinsic biodegradability or not. And these PM compounds, they're truly persistent, right? It's not a bioavailability issue in that case. But then you have the compounds that are higher KOC compounds and are also persistent, and there sometimes it is a bioavailability issue rather than an intrinsic persistence issue. So what is your opinion on this? Are these two kinds of persistences potentially, are they of equal concern? Or, I mean, obviously we have to deal with them very differently. But
That's a tough one. In principle, I would start off by assuming they were of equal concern until you could have some kind of weight of evidence approach in addition to like the standard approach to show why the standard approach may not work for this case. I'd be open to that, like as long as it's successfully shown by the available data. Yeah, and then that could be taken further towards whatever the harmonized persistence definition is. So in special cases, there could be different reasons to conclude persistence or not persistence. Yeah, but we have to have that standard to start the conversation.
Okay, so then we actually got a question from the online audience, so I will make that the last one because we also have to finish off. And it's a person called Karitos Apiris. Involving social scientists and psychologists to understand consumer behavior is scientifically very interesting. However, consumer behavior would not necessarily align with the attitude as decisions would be subject to their resources, time, knowledge, financial capacity. So would taking the pressure off the consumer and re-incentivizing the use of alternatives in the production phase be a better way forward?
Yes, I think so. It's just that, yeah, but these are complicated questions, so it's always the push-pull. I don't know if it's the producers, because sometimes it is, you know. I was reading this work by Rebecca Altman. It was showing how much work the oil and gas industry had to do to sell plastics at the beginning. Nobody wanted to buy it. But then eventually people bought it and they found out, oh, you can use it for all these things. But originally there's no interest. And so there can be push or pull, and sometimes it can just be people demanding. So now we're at the opposite. Now we're saying people don't want to use single-use plastics anymore. So that's having a different effect. So push and pull can happen on both sides. And I do think, but to answer that question, I do think getting the producers is probably more efficient than trying to get society to change.
Okay, super. Then I would like to thank you very much. And I think we should all give you a hand.
Thank you very much. Thank you. Toxic-free hierarchy, ladies and gentlemen. Toxic-free hierarchy. Okay. Okay. Thank you. Thank you very much.
We should also say that there are a number of posters on the PMT and vPvM and also on persistency, so please have a look at the programs and out there in the hallways as you go out and have a nice afternoon. Thank you.
0 PM. Zero pollution of persistent and mobile substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.